So as I said, here are the statistics. The maximum was 79 out of 80. The minimum was 41. The mean was 64. The median was close, 65. And the standard deviation was 9.5, basically. Okay. Most people did well on the first question, and on the second question, and on the last question. But the one with the table, that was the one that gave most trouble to people. So we'll talk about that later. I think it's better to start talking about exam number 2. And then if we have time, we'll talk about that. Okay? All right. So let's go over the solutions of the sample test. I uploaded it in Blackboard. Hopefully you've had some time to look at it. And so you're ready to ask me questions. Okay, so let's start first. And by the way, this sample test, how many of you try it? What do you think about it? It's a little long for us, and it was on purpose. So I gave some of the problems have more than what would be in the exam, so I could cover a little more, okay? So you have a little more to see, all right? Okay, so let's start with the true-false question, the first one. All right, the first one says, applying the half transform to the half transform of an image will return the original image. That is, applying it twice is the same as not applying at all. True or false? False. Second one. To find a curve using the half transform, it is not necessary to have a parametric equation of the curve being sought. True or false? True. So the generalized half transform allows us to do search for curves even though we don't have the equation. Number 3. See, when looking for a line in an image using the normal parametrization of the line, rho equal x cosine theta plus y sine theta as a half transform, either rho or theta must be positive. False. D. Segmentation using thresholding usually works poorly because histograms do not provide spatial information. True or false? True, right? In the histogram, you put all the pixels in a bag, and you forget who is next to whom, okay? So you don't have the spatial relationship between the pixels. E. If an arbitrary shaped snake is dropped in an homogeneous image region, the algorithm snake will not be able to move it. True or false? False. What will happen with the snake? Well, it's a closed snake. Sorry, I should have said closed. So what will happen to it? Yeah, it will shrink to a point. F. The energy functional of a snake depends on the shape of the snake, but is independent of its location on the image. Say louder. False. Why is false? This is the gradient of the image. So the gradient attracts the snake. So if there are different gradients, the snake will move differently. G. Segmentations using region growing and merging can result in under-segmented images, that is, too few regions. True or false? True. If you keep growing and growing, and you don't split, right? You don't backtrack. You have the danger of growing too much and merge two regions that shouldn't have been merged together. Okay. H. Hysteresis thresholding is used to thin edges. True or false? False. What is it used for?
Used for like finding edges that are kind of like smaller, I guess.
Weaker.
Yeah.
Yeah, you are filling gaps and linking edges that are weaker. If I wanted to have, what part of canyon edge detector does the thinning of the edges? There's, yeah, non-max suppression. Okay. I. The Laplacian operator, second order derivative operator, is useful in calculating the direction of an edge. False. It's a scalar, it's not a vector. We lost the orientation information. Last one. Sobel operators approximate the second direction derivatives of the underlying image. True or false? False, right? It is the first order derivative. Okay. Now, I'm just noticing, like, this sample test, the true-false questions, it was a little biased to the beginning of the topics of the exam. Don't take that as what's going to happen, right? There could be questions of a stereo and other things in here, okay? All right. Let's look at the first problem, okay? And it's about the half transform. It has two parts, and actually each part is independent of each other. So you could do entirely the second part. We haven't done the first part, but really to know how to do the second part, you better know how to do the first part, because the first part is the easiest part. Okay. All right. So it says the vertices of a square are 0, 0, 0, 1, 1, 0, and 1, 1. So I'm going to give them names, even though. Okay, so I have this square, so this guy is 1, 1. And I want to use the half transform for lines using the parametrization. Rho is equal to x cosine theta plus 1 sine theta. And the angle goes between minus 90 and plus 90. And rho goes between minus 4 and 4. Okay. So part A gives this square and has two things. The first thing is to plot in parameter space the half transform of the vertices, the 4 vertices, the center, and the diagonals of the square. Okay. So I need the half transform of these 4 points plus the half transform of that point, and also the half transform of the lines. Okay? So first of all, I'm asking for 2 different types of units that we're going to do half transform. Ones are points, right? And so what is the half transform of a point? No, it's not a line in this parameterization. It's a trig function, right? And what's the parameterization and the half transform of a line? It's a point. Okay? So you have the 2 things going on there. Okay, so let's do that in order. So let's start first by finding the half transform of the vertices. So A is 0, 0. So that means that the half transform of that is what? What's the trig function for this guy? Anybody? Rho equals 0. So what we need to do is very simple. You take the coordinates of the point, you plug it in here in this trig function, and that gives you the half transform for that point. Okay. So when I'm plotting, I'm going to plot rho as a function of theta Okay, and so A, and I didn't bring my color chalk to it, but A is, let's see if it's unlucky. No. Okay. So this one over here is A. Okay. Next one, let's do B. B is 0, 1, so that means that the Hertz transform is, again, plug 0 in X, Y equal to 1, and so I get rho is equal to sine theta. Okay, so sine of 0 is 1, let's put it somewhere here. Sorry, sine of 0 is 0, but am I doing? Let's go. One, so that's A. B. C is 1, 0. So that's cosine theta. D is 1, 1. So it's cosine theta plus sine theta. So I'm going to sum this curve and this curve. So 0 plus 1 is 1. This should have been crossing at 45. This is D. Okay. Let's call this guy M. So what's the coordinates of M? Half and half, right? So rho is equal to 1/2 cosine plus 1/2 sine. So really what I need to do is scale this function by 2, right? So here, here. How do I, yeah, so. Now, how about the diagonal BC? What's the half transform of BC? It's a point, right? So what are the coordinates of that point? What do I need to know? Rho and theta, right? Okay, so how much is rho? Right, square root of 2 by 2. Okay, that's rho. And how much is theta? 45. So 45 and square root 2 by 2. Here, that point is, I call that BC. And that's a good thing because it's the intersection of the curve for B and the curve for C. Okay, so that's where it should be. Okay. How about the diagonal AD? Sorry, say that again?
I was going to say the same row and then negative 45.
The same row. Are you sure? Rho is 0, right? Well, remember rho what it is. Rho is the distance from the origin to the line. Okay? The line passes through the origin, so the distance is 0. Okay? So in fact, in here, when the line passes through 0, figuring out the angle is a little trickier, right? It's not well defined, okay? So the trick I have for doing that is I move the line parallel a little bit up or down, and then I see what the angle is, and that's it, okay? But also, we can look at it, the line passes through A, M, and D, right? So the half transform should be the intersection of those three curves that you already worked so hard to draw, right? So I have A is the horizontal axis, right? And then D is this one over here, right? So it crosses here. And M also passes through there, so that's good. So this guy is the half transform of AD, right? And it has rho equals 0, and angle is minus 45 degrees. Let's see if that makes sense, okay, with my trick, right? So I take this line, and doesn't matter, I can put it here or here, right? I just shift it a little bit up or down, right, perpendicular to the line. And now I measure what is the angle, right? And if I pick this guy, the angle is minus 45. If I pick this guy, then that's also minus 45. Okay, so it doesn't really matter which one you do. Just move it a little bit and look at the angle. And remember, rho is 0 if the origin passes through the line. Okay, so this is AD. AD has rho equals 0 and theta minus 45. Okay? All right. The next thing that this part has, it asks to find the half transform of the size of the square after it was rotated 45 degrees clockwise around the origin. Okay, so I'm going to take this square, and with an axis perpendicular to the origin here, I'm going to rotate 45 degrees that way. Okay? So, of course, you could draw the square and see where it lands and find the half transform there. Or what we can do is find the half transform of the size of the square before the rotation. And then we know how to rotate very easily, right? How do I rotate the half transform? Yeah, it depends on the advantage. In this case, I will be subtracting 45 degrees. So I either add or subtract an angle, depending whether I'm doing clockwise or counterclockwise. Okay? The rho does not change. Sometimes I need to change the sign. Okay? But the angle is just subtract. And I have to make sure, of course, I stay within this range. Okay? So I had to do model this. Okay? So let's do that. So let's have before rotation and after rotation 45 degrees clockwise. And I have on the size AB, AC, BB, and BC. Okay. So what is the half transform before the rotation of the side AB? How much is rho? 0. And how much is theta?
90.
How much is theta? I'm doing this one, right? So this is my normal, right? So how much is the angle? 0. Okay. So okay. After rotation, what will happen? I'm doing clockwise, so the angles are becoming smaller, right? And I'm shrinking 5, so I need to subtract 45. Okay, so AC, how much is rho? 0 again because it passes through the origin. And how much is theta? 90. Okay. This is a case, though, that it could be either 90 or minus 90. Doesn't matter. Okay. I'm going to put 90 because I'm going to subtract 45, so it's much easier that way. I stay in the range. Okay. So I do rho equals 0, theta 90, and then rho 0, theta equal 45. BD, what's rho? 1. And what is theta? Now is 90. Okay. So I go 1, and the last one is DC. Has rho equal to 1 again, and the angle in this case is 0. So you can. Okay. Questions? All right, now let's do the second part. As I said, the second part in this case is independent of the first part. And what it says is this. Using a range sensor, for example, a Kinect, okay, we had captured a 3D scene as a set of 3D points with X, Y, and Z coordinates in the sensor coordinate system. So my sensor collects all of these points. I have a cloud of points in 3D. They all have coordinates X, Y, and Z in some reference frame. Assume that the scene contains a single dominant plane, for example, the front of a building, at a known orientation, plus smaller numbers of other scene points, for example, trees, light poles, a street, etc., that are not in this plane. Okay? So I have a lot of points that are on this plane. This plane, even though it says it could be the facade of a building, I don't know the orientation of the plane, so it doesn't have to be really vertical. It could be any orientation. Okay? But what I'm telling you is there are a lot of points that belong to the plane, and then there are other points in the scene, but less, that belong to different planes, or they are not in the plane. Okay? So the first part of the problem asks to define a half-transform-based algorithm for detecting the orientation of the dominant plane in the scene. Specify the dimensions of the half space, a procedure for mapping the data points to the space, and how the plane orientation would be determined. Okay? So the problem is asking you to generalize the half transform that we just did for lines, but now going to 3D. Okay? So here we were finding lines in the image plane. Okay? Now we're going to find planes in the 3D world. All right? So here, the main thing that we were using was this parametrization. Right? And this parametrization was in terms of this angle theta between the normal to the line and the x-axis, and the distance from the origin to the line. Okay? So now I want you to think a little bit out of the box, not too far away, really, okay? But just expand your horizon and think about it. If instead of having a 2D picture with a line, now I have a 3D world with a plane. What equation should I use to find the orientation of the plane? And again, the orientation of the plane is given by the normal to the plane, right? So right there is a hint, right? There's a similarity to what I'm asking you and what you already know how to do, okay? So what I'm going to draw here is a reference frame in 3D, has X, Y, and Z, and then I have a plane in this world, yeah? And what I'm looking for is the orientation of that plane. So how do I formulate my half transform problem to solve this? How do I find, again, the idea is that we have a lot of x, y, z points, right? And remember, if you need to remember something about the half transform, is that it's a voting scheme, right? Your data votes for a line in the here, or it votes for a circle, or it votes for a curve. So here my data points are going to vote for the orientation of a plane. And if I have a lot of points that I agree on the same orientation, I have found my plane, right? Make sense? So how do I write the equation of this plane in a way that will help us doing this? I want to generalize this equation, right? I want to write an equation of the plane in terms of the normal, right? So do you know how to do that? I'm sorry? Not cross product, dot product. Yeah. So let's first do it here, okay? So let's write this equation in terms of the normal of the line, okay? So what is the normal of the line? Say I'm talking about this line over here. Let me clean my picture a little bit. All right? This is the normal of the line, correct? In this equation, where is the normal? Right? The orientation of the line is given by the normal here, right? Cosine theta, sine theta are the coordinates of this normal vector. Okay? It's a vector in this orientation, and not only that, but it's unit norm. Okay. So the equation of this line, we can write it. Rho is equal n dot p, where p is xy. Right? So n has cosine theta, sine theta. P has xy. When we do the dot product, any point on the line and this vector, what we get is rho. Right? This is this equation. Okay? Are you ready now to move to 3D? What is the equation in 3D? First, forget about this part. Can we write it that way? Yeah? Can we, right? So what I'm doing now is I take a point on the plane, right? I take a vector from the origin to that point. When I do the dot product between this vector and the normal, I will get the distance from the origin to the plane. So it looks exactly the same. But now P has x, y, and z. Okay? By the way, I know it's not included in the studying for this test, but we already used this when I was talking about the motion field of a plane. We wrote the equation of a plane like that. So we have seen it before. Okay? But again, it's easy to generalize from that to that. Okay? Now, there the normal was cosine theta sine theta. Okay? How about here? Let me draw the vector. to the origin. Okay. So this vector in 3D, sorry, I'm really bad drawing at 3D, but it has coordinates in this coordinate system, right? I can have this angle here, let's call that phi, and this angle here, let's call that theta. Okay? So what is the coordinates of this normal vector? How much is this? Oh, let me first ask, how much is this? This is rho, right? The distance from the origin to the plane. Okay? How much is this? Rho cosine theta, right? That's the z component. Okay? How about the x and y component? I have this guy, cosine phi, and this guy is the same as this guy here. And this guy here is rho sine theta, right? So in the x coordinate, I will have rho cosine phi sine theta. And in the y component, rho sine theta sine phi, right? I'm running out of board. I said, sorry, cosine phi sine theta, rho sine phi sine theta cosine theta. Okay? Now, is this vector the way I wrote it unit norm? What's the length of that vector? What's the norm of the vector? Do this guy square plus this guy square plus this guy square. What do you get? I get rho square, right? So this thing has length rho. So in the rho, I don't need it. Okay? My normal, my unit norm, normal has this vector. Okay? So now I know how to write the equation of the plane with this normal. Okay, so what is the dimension? What's my half parameter space, and what is the dimension of that space? How many parameters do I have, and what are the parameters? John? Right. So it's 3 dimensions instead of 2 dimensions, and I have rho, phi, and theta. Okay, so when I vote, instead of voting in an array, a 2D array, I'm going to vote in a cube. Okay? So how do I vote? I give you a data point x, y, z. How does that point vote? It's a 3-dimensional array, right? And so what I'm going to do is I'm going to scan, right, rho and theta, not rho and theta, sorry, psi and theta, the angles, okay? And for each pair of psi and theta, I'm going to plug in my coordinates x, y, z in this equation, and I'm going to get a rho, okay? That's how I did it in the 2D. Remember, in the 2D, the way I did it is I scanned theta, and for each theta I computed rho, and that told me where to vote. I'm doing exactly the same thing here now, but I have now 3 dimensions. So I'm going to scan, I'm going to sweep the angles. Okay, that's easier the way the equation is written here, right? I can scan the angles, plug in x, y, and z in the equation. That will give me a row. And that tells me where in the 3D space I need to vote. So we have the space. We know how to vote. How do I find the planes? How did I find lines here? The brightest point, right? I look for the place I have most votes. Same thing here. I just scan my cube now, and I'm looking for the beam, the cell, that has the most votes. And if I find one that has a lot of votes, more than the threshold, say, aha, all of these points agree. And then I know what the rho, theta, and phi are for that thing. And so I have the plane. Okay? So the orientation is given by phi and theta, and where is located that plane is given by rho. Make sense? Okay. All right, so the second part of this part is not related to the half transform, but it's related to RANSAC. Okay, so I ask you, and this is to be written with words, to describe how the RANSAC algorithm could be used to detect the orientation of the plane in the scene from the data points. So you use RANSAC in the project. We use RANSAC to find correspondences. We saw in class how to use RANSAC to find lines. How can I use RANSAC here? So forget half transform. It's no longer half transform. It's just I give you data points, 3D data points. Yes?
I need to randomly pick 3 points, combine them, and then check and see all the other points line up on the plane.
Exactly, right? Why 3 points?
That's how many times.
Right, that's the minimum number that I need to define that thing, right? So with lines, we use 2. With the homography, we use 4, right? In this case, I'm looking for planes. So 3 random points defines a plane. I find the distance of all the other points to that plane, and I count, and I do it many times, right? And once I get one that has a lot of points, I say, this is good. All the points that are more or less close to that plane I pick with the 3 points should be inliers. Everybody else should be the outliers, the trees, the car, okay? And then what do? I need to do one more step. I take all those inliers and I fit the best plane to those data points. Okay. Questions? All right. All right, so the third problem, or third question, second problem, says, it's about features detection and description. And it says, to give a mask that can be used to approximate the first derivative of a 1D image, and to apply it to the image given below. So the gray values are 56, 64, 79, 98, 115, 136, 132, and 133. Okay. So again, I'm asking for a mask that can be used to approximate the first order derivative. and to apply to this image. And in addition to show the result, indicate where edges could be detected and why. And I also tell you, ignore computing a value for the first and last image pixels. Okay. So how do I approximate the first order derivative? I'm sorry? So, well, for example, or pre with, so what I need to do is differences, right? And so here there are multiple answers for this problem. You could even do something like this, okay? Or something like this, or this and this. Now, in this case, because I'm only doing in one direction, putting the two doesn't get me much, right? We give the two in the Sobel when we're doing it like in 3 rows, and so we give more importance to the middle guy and less important to the one on top and one on the below. But here I have only one. So, you know, you could do it this way, but again, the two will not really get you anything. So, again, you can do this one or this one. In my solution, I use the second one, okay? And I'm saying, don't worry about the endpoint. So, you know, the output here and here, I don't care, right? And now what I'm going to do is slide that window, right? And where it fits. In my case, if I use a 1/3, it would be like that. And we'll do the difference. This guy minus this guy, and the output will go here, right? And so I'm really bad doing math in my head, so I'm going to copy the numbers, okay? You can bring calculator. All right, so it's 25, 34, 36, 28, 17, and 7. Okay. So I also asked to show where edges will be detected and why. So where edges will be detected. So it depends my algorithm, right? So if I'm looking for the maximum, it would be at 36. Or I could have something, for example, that says anything above a threshold, say 30, I would say it's an edge. And in that case, I will have a thick edge here, right? So that's what I was asking you to mark. All right, so the next question is a little more conceptual. It says, compare the Canny edge detector with the Laplacian of Gaussian edge detector for each of the following questions. So I asked for Canny versus log. Okay. And the first one is the order of the derivatives that they use. What order of the derivative uses Canny? Do you do something with your hand? First, yeah. So Canny uses first. How about log? Second. The parameters they use. What parameters does Canny take? Connor? Sorry, say that again?
The sum of the x and y gradients.
Say it?
The x and y gradients.
Oh, that's the input, but not the parameters. So, which parameters do I need to tell the algorithm?
Window size.
Sorry, say?
Window size.
Window size and what with the window? They go hand in hand. What do you do with that window?
That's sliding.
Yeah, but so what was Canny? How did Canny find edges? It was the first order derivative of what?
either civil or fluid?
The civil fluid is basically to do the first of the derivative. We do canning using a mask like Prewitt or Sobel, but it's a combination of two things. Is the enhancement of the edges, which is the derivative, but it's also a smoothing portion of it, right? So we know that when we take derivatives, it's bad with noise, so we actually smooth the image. So canning, what it does, what he showed is that the optimal filter that he was looking for was very, 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 very similar to the derivative of the first derivative of the Gaussian. Okay, so it's not the most efficient way of implementing canning, but you could actually smooth your image with a Gaussian and then apply Sobel, and basically you'll be doing canning. Okay, or you could convolve directly with the derivative of a Gaussian. Okay, so said Gaussian, the parameter that I need to give here is sigma of the Gaussian, right? So I need the sigma, the smoothing, how much is smoothing, which is related to the window. That's what I said, the window matters if they go hand in hand, okay? Now what else? Because canning is not just the smoothing and the enhancement, it's the whole kabuko. So what's, no? You talk about this when we did the true false question. We talked about two things. One, thin the edges, the other one was fill the gaps, right? So it was a non-max suppression, and then there was the hysteresis thresholding, right? And so for hysteresis thresholding, I need to give how many thresholds? 2. Okay, so I have low threshold and high threshold. Okay? So that's basically the parameters for canning. How about the Laplacian of Gaussian? What parameters do we need to get? If it has Gaussian in the name, I need to give C. Okay. Finally, which detector of the two is more likely to produce long, thin contours, and explain why? Canning, and why? The non-max suppression will do thinning, and the hysteresis thresholding will do long. So, all right. Okay, now part C is like the previous problem. It's a generalization of the 2D problem to a 3D problem. Okay, so you know how to do things in 2D. I want you to think in 3D. Okay, 3D sensors are becoming cheaper and cheaper and more useful and more useful. So like from the Kinect to the cameras in the iPhone X. So consider a 3D image where instead of having intensity values at pixels X and Y, we have now intensity values at voxels. Voxels is the 3D generalization of a pixel. Pixel is a 2D, and voxel is a little cube in space. Okay, so I have now a sensor that gives me intensity, okay, in a cube. So instead of having an image that's an array of pixels, now I have an image that it looks like a Rubik cube. Okay, it's a bunch of little cubes, one on top of each other, making a big cube. Okay, that's my 3D image. All right, so we know how to do corner detection here. You implemented that for the project. So now I want you to think about how you generalize that to detect corners in this 3D world. Okay, so I want to find where a shape has a sharp corner. Okay, how do I do that? So in the hardest corner detector, what we did was we have the corner matrix, right? It was how big that matrix was? 2 by 2. How big do you think is going to be the matrix here? 3 by 3. Okay. So what you're going to have is something that has the form U V W times a matrix times a vector U V W. Okay. In 2D, we didn't have just x, y, x, y. Okay, now we have third coordinate. And in 2D, what we did with this matrix was, how did we find if it has a corner or not? How do you find corners? Alex?
You came up with R.
R was one way, and before we talk about R, it was another way. Eigenvalues, right? So we found the eigenvalues of the matrix, which were 2, and we said that there was a corner if, what happened with the eigenvalues? Both have to be large. So the smallest of the two has to be large. For the R, it was a surrogate of doing that, so we didn't have to compute this. And what we did is we actually, again, compare this against a threshold. And R, do you remember how it was related to the eigenvalues? 1. The determinant, which is the product of the eigenvalues, minus some value, trace, okay, which is basically the sum, right? So the determinant of the matrix, the trace of the matrix, and we got this, and that was save us some work. We didn't have to find out that. Okay. Now we're going to do something very similar here, but first let's talk about what's inside M. Right? How did we build M for 2D? What were the 4 components in that matrix? It was symmetric, John.
So if you have the x and the y gradients for the image, it was ix squared,
Okay. So how do you think it's going to be for 3D? Just guess. You don't have to. Right. We're going to have the derivative with respect to x, with respect to y, with respect to z, and then we're going to have the pairwise elements and make it symmetric. Okay. So we build that 3 by 3 matrix, and then we do find the eigenvalues. Okay. And we're going to ask that all 3 eigenvalues to be greater than a threshold. Okay. All right. The last part of this problem is to describe how the SIF descriptor is assembled. So it says the SIF descriptor is a popular method for describing selected feature points based on local neighborhoods properties so that they can be matched reliably across images. Assuming feature points have been previously detected using the SIF feature detector. So we know where we have a feature and we know the scale for that feature. Okay. Briefly describe the main steps of creating the SIF feature descriptor at a given feature point, and also name 3 scene or image changes that the SIF descriptor is relatively insensitive to. Okay. So anybody remembers how the SIF descriptor was made? No? So basically we found a Harris corner, a place that, you know, is interesting, okay, because we have this moment, this matrix of gradients that has large eigenvalues, okay, and we actually figured out also what the scale is, okay. So we have a scale size around that. So what it means is that we take this image and we have to either shrink it or expand it in the pyramid to have that scale. Okay? Then what we do is we take a neighborhood around that feature at that scale. Okay? And this neighborhood, it has 16 by 16 size. Okay? So that size is fixed. And then we have these little cells, which are 4 by 4. And within those cells, what we're going to do is compute the histogram of the orientations of the gradients. Okay, so we have gradients here in those 4 pixels, right? And we want to count how many are 45 degrees and how many are at 0 degrees and how many are at 90 degrees. So actually what we do is we have the orientations quantized, and we have actually 8 bins for the orientations. And we count how many we have. Okay? So we're going to have 16 histograms of orientations, one for each of these cells. Okay? Now, the histograms of the orientations are computed not absolutely orientations, but they are with respect to the orientation of the feature. So it's relative orientation. So we know what the orientation of the feature is. We know what the scale of the feature is. And so we're going to compute these histograms based on, okay? So I have now 16 histograms, okay? Each of these histograms have 8 bins. And we assemble now a long feature vector that's going to have 16 times 8. Okay, and that's my descriptor. One more thing I forgot to mention is when we do the histogram and we count the orientation, we just not count, one per pixel orientation, but we make that count in the histogram. We weight it by how strong the edge orientation is at that place. Okay, so it's a weighted histogram. Okay, so if I have a very strong edge, that counts a lot in my bin. If I have a weak edge, doesn't count. Okay, so that's my descriptor. Okay, now, given all the things I explained about the descriptor, how I have the scale of the feature, I have the orientation of the feature. Okay. When I build this descriptor, this feature vector, which is now what I'm going to be using to find matchings on the other image, okay, what kind of invariance do you think this feature has? Right? Does it change if I change the orientation of the image? If I rotate the image, will this descriptor change? No. Why? Because I use relative orientation. Okay. Will it change if I change the size of the image, if I zoom it? No, because I did it at the appropriate scale. I found the scale using the feature. Okay. Will it change if I change the illumination? If I add a constant to every pixel value in my image, will this change? No. Why? Because the gradient is differences, so it's not changing. Okay? Now, if I make my image brighter by multiplying the pixels by a constant value, will it change? The way I describe it, yes, because I missed one last step. The last step is you take this vector and you normalize it, you make it unique norm. Okay, and now we get rid of that constant. Okay, so the SIF descriptor is relatively, it's not, it's an approximation, but it's relatively invariant to viewpoint changes, rotation, translation, scaling, and illumination. Okay. All right. Let's do the last problem. So the last problem is a stereo problem. It has a room with the usual dimensions. The world coordinate system is in this corner. This is the z-axis, x, y. And there are two cameras looking down. So this is camera 1, and here's camera 2. They both have optical axis looking down, C1, C2, and Y. And the central projection of camera 1 with respect to the world is located at 2, 2, 4. And for camera 2 is located at 4, 3, 3. Both cameras have the same focal length equal to 1. And I think that's all. All right. So part A asks to basically find the epipoles. It says let E1 and E2 be the epipoles in camera 1 and 2 respectively. Find the camera coordinates E1, 1 and E2, 2 of the epipoles expressed in their respective camera systems. Okay. So what that says is that when I find the epipole for camera 1, I want the coordinates of that epipole expressed in the reference frame of this camera, and the epipole for this camera expressed on the coordinate system of this camera. Okay, so, and the notation I'm using here is that the subscript tells me what is the coordinate system I'm using. So this is epipole 1, meaning epipole in camera 1, expressed in camera 1. And this is epipole 2 in camera 2, expressed in the coordinate system of camera 2. Okay. How do I do this? Connor?
Find the expression of the line of the vector passing through the origin of camera 1 and camera 2. And find where that line intersects the image plane.
Yes. Can I do that in a more compressed way? That's the procedure. But what is it I'm doing with doing that? I'm finding what? I'm finding the. Well, yeah, I'm finding the epipoles. Yeah, but no, I'm finding the image of what? I'm finding the image of the center of projection. Okay. So what I need to do is, let's say I want to find the epipole of this camera, in this camera. So what I'm going to do is find the image of C2 in this camera, which is exactly what you did. That's the procedure. I would take a ray from here to there, intersect with the image plane. That will give me the epipole, right? But I can do that easier, right? Because I know how to find the image of a point, right? So what I need to do is find the image of this point. How do I find the image of this point? I need the coordinates of this guy in this coordinate system, and then I can apply my nice equations, right? That says u1 is equal to f x1 divided by c1, and v1 is f y1 over c1. Okay? So if I have the coordinates of the point I'm trying to project expressed in the camera coordinate system, then I just apply these equations and I'm done. Okay? I don't have to find the line and intersect because we already did the math for doing that, and we figured out that these are the equations. So the work I need to do, though, is express this point in this camera coordinate system. Okay? Can we do that easily? these two cameras, the way I gave the stereo setup, is there a rotation between them? No, right? No rotation, so that's easier. There is a translation, okay? So what I need is that translation vector. Okay. What is that? What's the translation vector? So I can do the difference of these two guys, right? But that will give me the vector expressed in the world coordinate system, because these are world coordinate systems. Right? So I have to be careful. I can do the difference between the two, right? But then I have to check which coordinate corresponds to which coordinate in my camera coordinate system. Okay? So the translation from here to here expressed in this coordinate system is equal, in this case, to 1, 2, 1. Okay. I'm going 1 in the x direction. I'm going 2 in the y direction, and 1 in the z direction. Okay. Now, if this is not so easy for you guys to see it from the figure, you can. It takes a little while to squint in your eyes and trying to figure out what that is. The other way of doing it is to find the way of going, for example, from the world to camera 1 and from the world to camera 2, which we know how to do that by inspection very easy, right? And if I know how to go from the world to camera 1, I also know how to go from camera 1 to the world, right? So now I can go from camera 1 to camera 2 by going camera 1, world, world, camera 2. And you can also do it that way. Okay? You should try it at home and see that you can get the same answer doing it either way. Okay? All right. So now that I have my translation vector, now I have the coordinates of the second camera expressed on the first camera system. It's going to be equal to what? One, 2, 1. And the camera 1 expressed in the second coordinate system is going to be? Yeah, -1, -2, -1. Okay. So now we can find the epipoles, right? I apply these equations to this point and gives me this guy. I apply this equation by set of 1 with 2s to this point. It gives me this guy, which is what I was asking. Okay, so E1 in camera 1 is equal to 1, 2, 1. And E2 in camera 2 is equal to also 1, 2, 1. Okay. Very clear here? Okay. So now part B asks the following. It says that the cameras took a picture of a fly flying in the room, somewhere here. And I tell you the image coordinates in the first camera of the image of the fly. And I tell you that that's at location 0, 2, 1. Okay? So both cameras look at the fly. They both take a picture at the same time. It's a stereo system that is synchronized. Okay? And I'm telling you where the image of that fly landed in the first camera. Okay? And I tell you that coordinates of that point in the image plane of camera 1, right? The third coordinate is equal to 1. The focal length was 1. And it happens to be at 0, 2. Okay? So now the problem asks to find the equation of the epipolar line containing the fly in the second camera expressed in the camera 2 coordinate system. Okay? So remember how the epipolar line was useful was exactly for that, right? If I have 2 images on a stereo pair, and I have a point here that has a fly, right, in camera 1, and I want to find the correspondence of that guy, what I need to do is find the epipolar line, and somewhere here, the other image should be. That's how I find the image of the fly. Right? So right now when I'm telling you, I have this guy, you have done the work here on part A, and now I ask, give me the equation of, actually first I ask for the epipolar plane, and then part C is asking for the epipolar line. Okay? So right now I want the epipolar plane. Yes?
The previous part,
Yes.
I'm really missing something, but it asks for, does it find the camera coordinates E11 and E22 and the epipoles expressed in the respective camera systems?
Yes.
Isn't that saying that's finding the epipole of camera 1
In camera 1.
in the camera 1?
Yeah.
Right?
Yes.
But the center projection of
So,
one in the camera 1 plane is going to be 0.
no. Let me change that picture. It's kind of hard to see. Okay, let's go back to my regular stereo thing. Okay, and what I'm saying is, let's make my image plane bigger. This is epipole 1. I'm asking you to find the coordinates of this point on this plane expressed in this camera coordinate system. So that's what we did. We took this guy, expressed that guy in this coordinate system.
But wouldn't that be E21?
This is, I call E1 because it lives in camera 1.
Oh, okay.
Okay, that's the convention I'm using. I took the projection of the other center and I find it in this camera. Because it belongs to this camera, I'm going to call it E1.
Oh, okay.
And then I'm going to put a supra in 1 because I want the coordinates of this guy expressed in this coordinate system. Okay. So right now, what we do have in this diagram, this is what I have. I have E1 in this camera, I have E2 in this camera, and now I'm leaving here a point F11. And this part of the problem is asking for the epipolar plane that contains the fly expressed in this coordinate system. So I have 2 coordinate systems I can work with. I'm asking, give me that plane in the 3D space, but written with respect to this reference frame. Okay. So how do I define the epipolar plane? The epipolar plane contains the baseline. So it contains the centers of projection. It contains the epipoles. And what else? The fly, right? So this is my epipolar plane. That's what I'm looking for. Okay? Because so far, all these 4 points, they're all aligned, right? So just, I can use all 4 of them, but I don't have a plane because they're all in one single line. I need one point that's outside of the line. And that point is the fly. Okay? The fly in the world also is on that plane, right? But I don't have that. But I do have where that fly image is. Okay? So I have a bunch of points on that plane. I just need to find the equation of the plane. And the hint that the problem gives is find first F12. And F12, what it means is this same guy in this camera, but now expressed in the other coordinate system. Because I want the plane expressed in this coordinate system. So I want all my points expressed on this coordinate system. Okay? So what I need to do is take this guy and change the coordinate system to this guy. Okay? So here I just erased what I needed. I had F1, 1 was 0 to 1. So how much is F1, 2? It's a change of coordinates, right? What's the relationship between the two coordinate systems? This translation that we had before, right? So I need to apply this translation to that. So this becomes now -1, 0, 0. Okay? I subtract 1, 2, 1 from this guy, and that gives me the coordinates of this point pressed on the other camera system. Yes?
For going back to part A, for the n-coordinate of 2 on the top A,
Yeah.
that'd be -1, 2, 1.
No, because when they divide by -1, the minus signs cancel. Right? So let's do the image of this guy. It's -1, F -1 divided -1.
I'm just asking about the n-coordinate.
This guy. That's exactly what I'm saying. Okay? I'm taking the image of this guy. How do I take the image? I do F, first coordinate, divided by the third coordinate. And F times the second coordinate divided by the third coordinate. So the signs cancel out. So both epipoles end up having the same coordinates. Okay. All right. So now here, I have this point expressed in the coordinate system I want. And I need 2 more points, right? And then I have my plane. So one easy one is the origin. I know the origin needs to be on that plane, right? And the third point could be, for example, this guy that's already expressed in this coordinate system. Okay? So now I have, I'm looking for a plane of the form ax plus by plus cc plus d equals 0, and these points need to be all on the same plane. So 0, 0, 0 in the coordinate system 2, -1, 0, 0 in the coordinate system 2, and my epipole 1, 2, 1. All these 3 points need to belong to this plane. Okay, so just plug it in, right? So if I plug 0 here, that tells me right away that D is 0, right? So out. When I put this here, which other coefficient is 0? A. Okay, so now my plane looks by plus cc equals 0, and I already used this guy and this guy. So let's use the third point. Right? So the third point says that b times y, so that's 2b, plus c times z, that's 1, has to be equal to 0. So c is equal to minus 2b. How do I find, do I need one more equation? Connor? So I have 4 things I didn't know here, right? I got rid of D, I got rid of A. I have 1 equation for B and C. Do I need one more equation? Not really. Why not? If I multiply this equation by 500, is a different plane? It's the same plane, right? So this is really up to a constant. So I can make, for example, b equal 1. Why not? Okay, so if I say b equal 1, then c is equal to minus 2, and I have the equation of the plane. Okay, so my plane is y minus 2z equals 0. Okay? That's the equation of the bipolar plane expressed in the coordinate system of camera 2. Okay, now the last part of the last question of the exam was find the corresponding epipolar line in camera 2 expressed in the camera 2 coordinate system. So how do I find the epipolar line? I need the intersection between what and what? Into the image plane and my epipolar plane I just found. And what's the equation of the image plane? C equal 1, right? So this and c equal 1 tells me that y is equal to 2. That's the equation of the line on the image plane camera 2. Okay. And now that I have this, I could go and find for the fly, look for the phi, search for the fly on that line. Questions? Yes?
Yeah, if I still didn't get to how did we get the translation 1-to-1 in the first part?
Okay. Can I raise the plane part? So this point over here, the central projection of the first camera, has coordinates 2, 2, 4. So let me get it down here. So in the world coordinate system, this is 2, this is 2, and that was 4. And this guy has 4, 3, 3. So when I go down here, you can down here, this is 4. This is 3, and then this over here is 3. Okay. So for example, you can see that this guy is 1 unit below this guy along the z direction. So the translation along the z direction is going to be 1. Okay. Now, in terms of the x direction, this guy is at 2, and this guy is at 3. So it's 1 in that direction along the x direction. And for the y, this is a 2 and this is 4, so it's a translation of 2. So that's my vector 1, 2, 1. Okay. So again, I saw it that way, but what I was saying is I can also do it mathematically if that's hard. And what you do is you have a way to go from the world coordinate system times a matrix. That gives you the coordinates in the first camera system. Okay, so I know how to go from W to C1. Okay, so can you write it down by inspection? Right, so it's just x minus blah blah. And if I have that, I also know how to do the other way. I can from here I can write down x, y, z is equal to a matrix times x1, y1, z1. Okay? So I know how to go from camera 1 to the world. And I also know how to go from the world to camera 2. Right? So these matrices are all different, of course, right? But so what I have to do is, instead of putting here x, y, and z, I put x, y, and z from this expression that has this matrix times x1, y1, z1. Right? And so now I have an expression that relates x2, y2, z2 to x1, y1, z1. Okay? And because in this case it's all translations, it's also very easy to do the math. It doesn't take long. Or you can be sneaky and just look at the picture and make sure that you don't confuse the axes and you write it down by inspection. Okay? Any other questions? Questions about the homework? No? All right. If not, I'll see you Friday for the exam. Again, closed book, closed notes. You can bring 2 pieces of paper, 8.5 by 11, both sides, as small as you can read. You can bring calculator, okay? And I have office hours right after class. I will be in the lab, not in my office, but in the lab. So if you need to talk to me, follow me to the lab and you can